Okay, thanks for joining my talk today to talk about powders and powder flow rheology. I'm Dave Vanderweel. I won't go through this full bio. I work for Anova Analytical. I've been working in materials research for about 25 years. My background is chemical engineering, surface chemistry, and catalysis. Quickly, NSL is a testing laboratory, actually two laboratories here in the Cleveland area. We work in a wide variety of industries such as aerospace, additive manufacturing, oil and gas, energy. And one of our core capabilities is our particle characterization laboratory. So today I'll go over what I'm going to talk about. I'm going to start out discussing differences in various powder flow techniques and do some comparisons between them. Give a general description of what I mean by avalanche rheometry. Also go through quite a few examples of avalanche rheometer data versus other techniques for use a couple different applications. One, comparing similar or dissimilar powders, just side-by-side comparisons, and then also examining the impacts of powder reuse and how rheology can be characterized for those systems. And then at the end, I'll touch on some of the information that's out there in terms of variability in the rheometer data from avalanche rheometers. I also want to introduce briefly this concept of relative standard deviation that I use throughout these slides. I don't use it in the traditional sense with a large data set, but instead I often use it just to compare two different values. And I do this because I'm comparing a lot of different techniques with a lot of different units, and RSD is a kind of a simple way just to show relative differences in numbers of different magnitudes. And I've also arbitrarily chosen 10%, anything greater than 10%, suggesting a significant effect, and at the same time, anything below 5% being somewhat insignificant. But again, those definitions are arbitrary. So looking at the different flowability techniques that are applied to metal powders, I think most people are familiar with the conventional static techniques, such as flow indices based on density, angle of repose, in both the Harney-Hall flow rate and the Carney flow rate being fairly standardized within ASTM. Another technique that people talk about are these quasi-static or quasi-dynamic techniques, such as shear cells or the impeller-based systems like the Freeman FT4. Again, that is a technology that's part of F42's push to look at standardization. Currently, there's no standards within AM for that technique, although there are for other fields. And same goes for the avalanche or drum rheometers. These are a dynamic rheology technique. And again, F42 is working on quite a few standards that involve that method. Comparing these, I categorize them again here as static, quasi-static, and dynamic testing. One of the defining characteristics is the stress state of the powder during the test, whereas the Hall and Carney static flow and the dynamic avalanche are low stress environments. The quasi-static techniques are generally moderate to higher stress, and many authors have talked about the suitability of low stress state techniques being better for AM powder bed spreading. The different techniques all have different sorts of data. Some of them are quite comparable, some are not. They provide qualitative data, semi-quantitative data, and then a variety of true quantity values that I'll go over today. One of the advantages of the avalanche and drum rheometers are they're fairly simple to use. Not quite as simple probably as a Hall funnel or a Carney funnel, but pretty close. The data interpretation can be pretty simple, although you may have to set up the parameters a little bit, so it can vary a little bit, but I would never say it's complex. And the parametric analysis is capable, just like it is with quasi-static methods, you can actually run multiple conditions during a single test. So that's nice to have that ability as opposed to just having to run multiple tests in the case of static flow methods. Talk a little bit about the resolution of static flow testing. In this reference from last year, 4 different types of powders of different densities were recycled from 3 to 38 times. And we looked at the Hall flow rate, and you can see that the variation between virgin and recycled flow rates is pretty small, less than 10% in general. Still, that's within the detectability of the method in some cases. Hausner ratio wasn't nearly as good. In most cases, categorized what they would call excellent flow, with the exception of the aluminum silicon magnesium alloy that had slightly higher Hausner ratio, but you see those deviations are all very small, so it's hard to distinguish between those virgin and recycled powders with Hausner. And Car index in this case, or compressibility index, is actually a little bit better. You see in a couple of the powders, we got better resolution, but the interesting thing is that the trends were actually opposite for Car index versus the Hall flow rate, whereas they showed the Hall flow rate improved for 3 of the 4 powders. The Carney index actually suggested worse flow for 3 of the 4 powders. So only for the Inconel powder did it correspond. And this gets into variability. Again, if you look at that same data for the Inconel Hall flow rate and look at a different reference I have here from 2017, you can see in some cases almost a factor of 2 difference in reported rates, going both for virgin and recycled for a comparably sized powder of Inconel 718. So this is another issue, is lab-to-lab variations. This is another example of variability with static techniques. This is a Carney flow test series where a powder was dried, aluminum powders were dried and then exposed to some humidity levels, and the Carney flow rate was monitored as a function of time. And you see there was some nice trends here the authors presented, but the problem being that there's a lot of scatter during those trends. So at any point in time, if you just collect one of those data points, it's going to have a hard time comparing it to another one. Now the quasi-static flow testing, I won't talk too much about this technique today. This is one paper from earlier this year, showing 5 laboratories that examined the variability in the technique. And you can see there's some huge variability between these standardized samples that these laboratories examined. And they did report that the variations were not associated with sampling or environmental conditions, and suggested some potential other sources. So this is definitely an issue we've seen before, and one of the reasons we look at the dynamic techniques. So Avalanche Rheometry, examples of this are the Granny Tools Granny Drum and Mercury Scientific's Revolution. Most of the data I show today is, I believe, on the Mercury Scientific Revolution, and that's the one we use at NSL. Both instruments are basically optical techniques where a backlighted sample drum rotates, and the digital imaging is used to analyze the powder movement. You can do quite a bit with this type of test. You can look at parameters such as the revolution speed, the fill level, and program in different parameters such as the number of test cycles or number of avalanches. And some of these conditions can be set up to mimic the conditions on spreaders in AM, such as a roller or a blade type coder. This figure shows how the software analyzes some of these. In cases of avalanche angle, it's basically just looking at averaging over a number of times, up to 100 different avalanches or so, the angle of the powder before or after or during the avalanche. And then things like surface fractal, it looks at the linear line comparison to the fractal of the actual surface to show smoothness of surfaces and how that relates to flowability. The basis for all of these parameters lie basically in the amplitude and frequency of how regular or irregular the avalanches that occur. And that's why all these techniques look at on the order of 100, sometimes more avalanches and average the results, because what they're doing is comparing not just one avalanche, but how all the avalanches spread out. And these strange attractor plots from a paper from last year shows a very good example of the basis for these types of measurements, and that more cohesive flow results in these very irregular avalanches and these strange attractor plots, whereas a more regular avalanche and a much tighter distribution there would correspond to something that flows a lot better. There's different parameters. The parameter lists in the software can sometimes look like too much, but really for us, we found that it comes down to maybe 4, 5, 6 different parameters that are most important. It's up to a user to determine what those are. But there's a few here highlighted that are fairly universal. Those are the energy, based on potential energy of the powder, various angles, and also some numbers to calculate shear stresses, and in some cases bed density during the rotation can be quite nice to know. And some people report good success with the surface fractal numbers. So one of the main uses for Avalanche Rheometry is to compare between powders. I'll go over a few examples of that here today. Here's some 316L stainless steel, gas atomized and water atomized powders. And you see for the Hall flow case, there was quite a difference there. Basically, one flowed and one did not. And the avalanche angles both passed the internal spec for this particular reference. And then when you look at the printed specimens made from these powders, again, versus their comparative specs, I won't go over them all but one of them passed. And so you can see here that while the Hall flow rate may have indicated that one of the powders might not be suitable, the avalanche angle from a rheometer, powder rheometer, actually showed that yes, they're both acceptable based on this company's internal specification. And the printed specimens verified that they were both able to make suitable specimens from those two powders. Another example is for a couple cobalt alloys, probably biomedical alloys used for medical purposes. Here again is a gas atomized and water atomized, and you can see obvious differences in chemistries from the production processes. If you look at the Hausner ratio in this case for these two, they're basically very close, only about 5% deviation between the two. Whereas if you look at the avalanche angle or the avalanche energy, a much higher difference showing up between the two. And then when they looked at the physical properties, mechanical properties of the parts made from these, you can see that depending on the conditions of the build, they were able to see differences in those strengths. So they can make both work again, but once again, the dynamic rheometer is able to distinguish between them much better than traditional techniques. Here's an example with 3 aluminum powders. You'll see that primarily the difference here, looking at them from the powder properties, is that the powder A is a much larger size powder than the other two. Looking at the static flow tests, again, we have this flow, no flow situation in the case of the Hall flow, so it doesn't really help us too much. The Hausner ratio varied very little between the 3 powders, almost not enough to say there's a variation. But the angular repose in this case was pretty substantial, and that's actually what these authors used as a basis moving forward for comparing them. Again, they tested the Freeman FT4, I believe, and found little variations in that data. And then they tested with the Mercury Scientific Revolution again, and for 2 of the 3 parameters saw some pretty substantial differences in the properties of those powders. And so based on that, all the methods were able to identify the worst flowing powder, whereas the static flow and dynamic flow did both identify A as being a better flowing powder, you can see some differences there in the resolution between the ability of how they could distinguish those better. So the authors in this study then did an Anova analysis by varying the parameters listed here of layer thickness, recoater speed, the material the recoater is made out of, and also whether it was a low angle of repose powder or versus a high angle of repose powder. And based on their results, they presented the fit for those different Anova tests. And you can see that once again, the dynamic flow tests all passed. Their R-squared requirement showed very strong correlation, as did the angle of repose. The same group then developed their own spreading spreadability test using image analysis from both the top view and side view. And again, they got some really good results and showed powder A, and here I've removed powder B just for clarity. They showed powder A again was the best spreading. So that backs up what the dynamic flow tests and the angular repose showed. And in their case, the RSD for those were very substantial. So it was a very clear difference in those powders for those two. Another example of aluminum powders, this is an example that shows both similar and dissimilar powders. A and B in this case are very similar in many ways, whereas powder C had a much finer particle size distribution. And when they did their static flow tests, again, the pore flowing powder C was pretty clear, but for the most part, powders A and B were almost indistinguishable, with the exception of the angle of repose. The dynamic flow tests in this case were done on a granny drum under a first set of conditions, showed much better resolution of powders differentiating between A and B using one of the two parameters, the cohesive index. And then as they changed those parameters and increased the revolution speed of the granny drum, you see that resolution actually improved, and they were able to show very strong distinction between not only A and B versus C, but also just A versus B. So this shows that the parameters programmed into the rheometer can improve your results once they're optimized. This group then again did those spreading tests and came up with spreading density. In this case, the spreading densities were almost indistinguishable. So A and B again were very similar, whereas C was obviously not as good. This comparison here was for Inconel 625 materials. These three powders here again, two of them are pretty similar. One of them is quite different. You see powder number 2 is a very fine powder, and so I've graded that out, and for the most part, I don't really look at that one. And so the RSD comparisons here are strictly for comparing powder 1 to powder 3. Static testing, again, one of them flowed, the other did not. Hausner ratio, they're almost indistinguishable. Using the quasi-static Freeman testing, they were able to identify the poorly flowing powder, but the properties for the two other powders basically overlapped or were not distinguishable. In the dynamic flow tests on the mercury scientific rheometer, about half of the parameters there that they examined showed moderate to strong ability to resolve a better flowing powder in agreement with the static flow test, in this case the Carney flow rate. And again, they all identified the poorly flowing powder pretty easily. They then performed some different builds using different laser energy densities on SLM, and you could see that they're basically able to produce pretty good parts from either set of powders just by varying the build parameters. So this suggests that actually in the case of tests where the variation wasn't very significant, that may actually be correct, because in this case they were able to find that both powders 1 and 3 were suitable, maybe just under different conditions of the build. One final thing on comparing powders here is kind of interesting recent patent on powder use for additive manufacturing from Heraeus. they actually introduce a Q factor here that is a ratio of the avalanche energy to the median particle size diameter, and they set a ratio of 0.8 as being distinguishing in this case. They then provide data here showing examples where that Q factor is acceptable or not acceptable, and then some relative density and SEM images showing poor and good porosity resulting. So this is really interesting. It's the first time I've seen any patent built around this avalanche type rheometer data. So it'll be interesting to see where this goes. Effects from product reuse. This goes back, a lot of people have seen this. This is an image here from some earlier papers on changes with improvements of mechanical strength of printed parts upon recycle. But for in terms of powder flowability, that's been something that's been demonstrated earlier in titanium and various stainless powders and confirmed more recently. I'll talk about an ASTM B09 powder flow workshop and some other recent testing. The 2019 workshop involved the three instruments, the Freeman grinding tools and the Revolution, two different materials, three different powders, a virgin, recycled, and one that's a 50-50 blend. And each lab, they tested it, repeated the test 3 times. Looking at both the relative standard deviation between the virgin and recycled powders, as well as a correlation coefficient for that series, virgin to blend to recycled. You can see some trends there in the properties of the powders themselves, but also then looking at Hausner and Hall flow, very mild, very slight trends. You can say that those are almost identical in some cases, but they are slightly detecting changes. Good correlations in the case of the Hausner flow, but very slight 1 or 2% variations between the two. That same data now this used the Mercury Scientific. They looked at avalanche energy, angles, break energy, and some other parameters, and you see moderate to very strong variations between the numbers going from virgin to recycled, but also in most cases very good correlation for the three. So this one clearly identified those trends. Coming up soon, the 2020 this year yet, you should see the results of an ILS round robin, where now the same study has been expanded and 3 different laboratories looked at each instrument and 4 powder samples with repeats. So we'll see that probably before the end of the year. Another case here is a 304 stainless steel powder reuse. Again, very marginal changes with recycle. You can argue that those are barely detectable. Here with the avalanche energy and angle, less clear, but still a moderate trend, at least in the avalanche energy, identifying the recycled one. And the authors gave some pretty good explanations for why that was the case. And then before I finish here, I talk about the variability in the avalanche data. You can see I summarized several of these with their standard deviations and then the relative standard deviation calculated from those standard deviations. So in this case, this is a true relative standard deviation from a data set. And you can see as flowability diminishes, the variability tends to increase. You see a lot of jumping around the data, but definitely the lowest variability is for the highest flowing powders and the worst variability is for the worst flowing powders. So there's a general trend there. And there's actually a publication from a few years ago that looked at 23 iron and nickel powders and showed this in a much clearer way. So definitely as flow diminishes, you'll see more variation with this technique, not unlike other methods. So to summarize, Avalanche Rheometry, I believe, shows much higher resolution data than conventional flow techniques. It oftentimes agrees with those techniques, but it's able to correlate much more clearly and show better resolution. The results are usually best done on a comparative basis, not as absolute values. It's very capable of identifying subtle differences in powders that the static techniques cannot, but it really excels at identifying trends in sets of powder properties, sets of powders. Although the list of parameters can look daunting, really it oftentimes falls down to a much fewer set of 4, 5, or 6 parameters. The ability to change the test conditions may add some complexity as we go to standardize these methods. As we've seen, that the test parameters themselves can affect the results. And so that adds a little bit of complexity when we try to define specific test methods. And as you just saw, the variability in the data increases as the floatability diminishes, not unlike other techniques. And as long as we have a lack of standardization within the powder sampling and conditioning, there's going to remain this variation from lab to lab. So that's something that needs to continue to be addressed within F42. All right, thank you for your time. I think I have 10 seconds left, so I hope we'll have time to talk to your questions.